Recently, contemporary Amperex Technology, CATL, has unveiled their first-generation sodium-ion batteries for commercial use. This news has created quite a buzz, as many have been eager to see a successful sodium-ion battery manufactured. After lithium-ion batteries becoming the standard for many years, sodium-ion batteries have started to resurface, making this news from CATL particularly exciting. In this video, we will discuss sodium-ion batteries, their current level of development, and their potential impact on the renewable energy market. Like lithium-ion batteries, sodium-ion batteries consist of a cathode, an anode, a porous separator, and an electrolyte. During operation, ions move between the cathode and anode to store and release energy. The primary distinguishing factor between sodium-ion and lithium-ion batteries is the materials used in their components. This is one of the major appeals of sodium-ion batteries, since they can potentially utilize the same engineering and production methods as lithium-ion batteries. As the planet's reserves of lithium is limited, and extracting lithium is not an easy nor environmentally friendly process, and other critical elements such as cobalt add additional environmental and humanitarian concerns. In comparison, sodium is much more abundant, with over 1,000 times more sodium than lithium in the Earth's crust. Additionally, it's far easier to mine. This makes the raw ingredient cost of sodium much lower. Since the early 20th century, researchers have been attempting to make sodium-ion batteries commercially available as an alternative to lithium-ion batteries. In 1968, the Ford company created a sodium-sulfur battery for electric vehicles composed of a tube of metallic sodium dipped into a tube containing liquid sulfur. Ford believed that a 350-pound sodium-sulfur battery could achieve between 200 to 300 miles of range for a 1,350 pounds car traveling at 40 miles per hour, with a minimum charging time of 30 minutes. Unfortunately, this type of battery only works at very high temperatures, between 300 to 350 degrees Celsius. This posed safety and durability issues for cars. For example, aluminum used in the container tubes would react with the battery chemicals, causing them to rupture at such temperatures. Molten salt batteries have yet to make an impact on mobile electronics, but they have several real-world applications. One of the most common uses is to provide power for guidance systems in missiles. Additionally, they are ideal for extreme environments. In 1985, South African researchers developed a new version of the molten salt battery, using nickel chloride and sodium tetrachloroaluminate. Ford sold the technology to a Japanese company called NGK, and now it is sold as stationary battery solutions for peak energy use and grid stabilization. The Zebra battery, as it was named, seemed full of potential. However, Sony introduced the lithium-ion battery in 1989. Its advantages quickly won over the industry, and research shifted focus. Now, lithium-ion batteries are the go-to for electric vehicles, stationary batteries, and mobile gadgets. However, in the 2000s, issues regarding the supply of raw materials arose, bringing new challenges to the industry. As I previously mentioned, natural sources of lithium are limited, and this cannot be overlooked if we are serious about creating a carbon-free economy. Furthermore, the intellectual property rights around lithium-ion technologies has created a complex legal landscape that makes it difficult for new companies to enter the industry. This has led to a renewed interest in sodium-ion batteries, which can be used at room temperature. Publications relating to sodium-ion batteries have been steadily increasing, and in recent years have even surpassed those of lithium-ion batteries. Batteries, especially prototypes, vary greatly from one another. However, scientists have recently discovered a few sodium-ion battery chemistries with high potential. The anodes are typically made from hard carbon. The electrolyte must be low viscosity, highly conductive, and electrochemically stable, and usually consists of sodium salts dissolved in organic carbonate solvents. Much of the recent research on lithium-ion batteries has been concentrated on the cathode, as it is the single most expensive component in the battery and is essential for its viability. A variety of potential cathode materials have been identified, with the sodium layered oxides being the most well-researched. These oxides have a layered crystalline structure, with metal oxide sheets surrounding sodium ions. Cathode materials used in sodium-ion batteries have been extensively studied, with many different compounds. However, contemporary Amperex Technology (CATL) has chosen to use an alternative option. The material they use is similar in its crystalline structure to lithium cobalt oxide, the original cathode material used in lithium-ion batteries, and is why it is seen as so promising. In the past few years, there has been a lot of experimentation in the field of sodium-ion batteries. This science has advanced quickly, and the first few products are beginning to enter the market. One of the first truly commercial-ready sodium-ion batteries is an 18,650 cell, created by the French research agency CNRS in 2015. 2 years after its establishment, in 2017, the agency spun off its research into a startup named Tiamat Energy. The long-term goal of the company is to create low-voltage systems for hybrid vehicles and to ensure French technological sovereignty. Fast forward to June 2020. Researchers at Washington State University and Pacific Northwest National Laboratory announced a more sophisticated sodium-ion battery. Its creators postulate that the battery might be able to reach a practical specific energy of 160 watt-hours per kilogram, which is comparable to current lithium iron phosphate batteries. However, it is essential to keep expectations in check, as sodium has a lower ionization potential or ionization energy than lithium. Consequently, sodium-ion batteries may have a lower energy density and operating voltage than lithium-ion batteries, and it is uncertain whether they can ever catch up to the performance of lithium-ion batteries. Aside from CATL, there are several other technology startups working on commercializing sodium-ion batteries. Faradion Limited from the UK, Ultrasabi from Sweden, Hina Battery from China, and Natron Energy from the US are a few of the notable ones. CATL recently announced their own version of the battery, boasting a unique porous structure for their hard carbon anode that increases cycle lifetime and enables more sodium-ion movement. As previously mentioned, the engineering and manufacturing procedures for sodium and lithium-ion batteries are similar. Consequently, CATL can benefit from this by incorporating its sodium-ion offering into their existing lithium-ion infrastructure and product ecosystem. However, it should be noted that the cost savings from sodium-ion batteries will not be significantly lower than lithium-ion batteries due to the shared preparatory processes. The majority of the savings will be from cheaper raw material costs. It has been estimated that end users could save 10 to 30% on their energy costs by using sodium-ion batteries compared to gasoline prices. Additionally, these batteries can be combined with lithium-ion batteries, which have a higher energy density, in one system. This integration of different battery types is an interesting concept for the future of energy storage. Despite all the talk of new and innovative battery chemistries, the reality is that many of these concepts do not end up being put into commercial use, and even fewer become widely adopted. One example of this is lead-acid batteries, which, despite having been around for 150 years, possess lower energy densities and toxic materials, yet remain popular due to their low cost and reliability. In 2020, global lead-acid battery sales totaled nearly $50 billion, demonstrating just how significant inertia can be. It is unlikely that sodium-ion batteries will be able to replace lithium-ion batteries in applications such as mobile phones and other electronic gadgets. However, they have potential in shorter-range electric vehicles and stationary power systems, where space is not much of an issue, and the lower energy density of sodium-ion batteries is not so much of a concern. Sodium-ion battery technology has the potential to revolutionize the energy storage market for solar and wind renewables. Small startups have already begun exploring this area, but Chinese battery giant CATL is taking a much larger approach. With their immense resources, manufacturing capabilities, and research and development experience, they are poised to make a major impact in this space. If successful, CATL will be able to bring sodium-ion battery technology to its full potential. I hope you have enjoyed this video. If you have, please leave a like or subscribe to the channel.